Okay, all right, webinar is being recorded. All right, now let's get started. So where do we want to start? What chapter? 8, 9, 10, or 11? 10? I saw some 10. Okay. And actually, before we get started, because it is so intimate in here, I mentioned before that if you've come to my office hours, I'll give you a gift. Who hasn't received their gift? A lot of people. Well, I have some here. So let's get these out. Here's the gift. There you go. There. Keep those hands raised. Yes. Okay. There you go. 2. You got 2. Because I want you to give them around so I don't have to. Oh, I like your Disney shirt. Yeah. And actually, I noticed at the talk, you sat next to my boss. Oh. My boss, the dude sitting next to you. Who else? Anyone else? Did you get one?
Oh, no, thank you.
Okay. Okay. We all got one? Okay. So hopefully this will help with your studies. So remember, for those of you on Zoom, if you come to my office hours, you can get a gift as well. That'll help with your studies. Because we just learned about activation energy, you know, doing homework and all that stuff. Having a periodic table nearby and having those molar masses, that's a high activation energy. It sucks to have to look stuff up on your phone. Yeah, so there you go. All right. Okay, so in order 8, 9, 11, 10. Okay, well, we're going to do 10 first because that is what people requested. So entropy, this is what we just went over today. And honestly, this part of the chapter is rather short. There's less questions probably going to be on chapter 10 just because we finished this chapter in basically one day. It was like split over to 2 different lecture periods. So let's do true or false, because entropy has a lot of ideas of a lot of conceptual ideas, right? Okay. And honestly, this relates to the first law of thermodynamics 2, chapter 9. So let's go through these. True or false? A combustion reaction always is exothermic and has a delta H, a positive delta H. Is that true or false? Well, 1, let's break this down. Are combustion reactions exothermic? Yes, they should be. Yeah. And do exothermic reactions have positive values of delta H? No, that is the definition of exothermic is a negative sign for enthalpy. The reaction releases energy. All right. So delta H is a negative value. And I know it's hard to wrap our heads around this. Yeah, it feels hot, but it gets hot because the reaction releases energy to you. You are the surroundings. The reaction is the system. You're just an observer. All right. So this one's false. A decomposition reaction always has a positive entropy change. True or false? Let's think about, honestly, just like draw it out. Think your way through it. What, like, just give an example decomposition reaction. A becomes 2B. A becomes 2 things. So entropy increases. So this one is true. True. All right. The second law of thermo says if delta S of your reaction is positive, the reaction is spontaneous. That one is false. And this is a common misconception. Students understand, yes, entropy increases for second law, but it's not of delta S of the reaction or system. It's delta S of the universe. So the law is when delta S of the universe is positive, the reaction is spontaneous. But the universe consists of both the system and the surroundings. I think I just got this question today from a student. I don't know if from you guys or 1220. I'll just say you guys are my favorite. You guys are no nonsense. Someone said, like, aren't all positive entropy change reactions always spontaneous? But that's not quite true. If this component is positive and this component is positive, yes, the delta S of the universe is positive. This will be spontaneous. But what if delta S of the system is positive, and we're subtracting or adding a really big negative number for delta S of the surroundings. In this case, this is now non-spontaneous because the surroundings is losing energy, right? Or the other way, that you can make a reaction that becomes less less entropy, that it loses, becomes more ordered. We can force this to happen as long as the surroundings increase enough entropy. Okay, we can force it to be spontaneous if it's this way. All right. Okay, so keep going. Delta S of your reaction is, so we're going to talk about it. If delta S of your reaction is negative, your reaction can still be positive, or spontaneous, if your surroundings is very positive. And that is true. We just said that, right? That adding a big number to a negative number can make the universe increase entropy. So that is true. The last one was false. All right. If your entropy change of the surroundings is very positive, the reaction is very exothermic. So let's take a moment and look at the supplemental information and just see what equations are given. All right, so here we give some equations. Here is entropy change of the universe, system surroundings. Obviously, the first law says this needs to increase for spontaneous reactions. But what's going to help us here is this equation, that your surroundings, the change of your surroundings, is equal to the opposite of the enthalpy of your reaction. I like to think of it this way. Exothermic reactions heat your surroundings up. When the surroundings get heated up, entropy increases. Versus if, your reaction is endothermic, it feels like it's getting cold. You're the surroundings, you're getting colder, your entropy is going down. So that's why there's that negative sign there. So if we go back to the question and recognize, okay, delta S of your surroundings is equal to negative delta H of your reaction over temperature, an exothermic reaction is negative. So a negative times a negative, yep, this is true. Delta S of your surroundings is positive. Your surroundings will increase entropy for an exothermic reaction because it's getting heated up. The surroundings are getting heated up. You're getting heated up. You are the surroundings. You are never the system. I don't know how it's like in physics. That's how it's like in physics? Okay. Well, in chemistry, you are unimportant. It's all about the reaction. Just keep remembering that. Because it's oftentimes, if you're going to mess up on this exam, it's a sign. It's because of a sign. And it's because you think for a moment you are the system. All right. The forward and reverse reaction occur. The system's at equilibrium. So delta E G equals 0. And that is true. I like to think, okay, your forward reaction is spontaneous. It's negative delta G. If the reverse reaction is spontaneous, it's positive delta G. So if neither are spontaneous, meaning we're at equilibrium, both of them are occurring, then delta G 0, because that's what separates positive and negative numbers. Okay, so let's look at increasing entropy for these substances. So there's many factors, mostly weight, complexity, molar mass. I already said weight. For these substances, because we're looking at 1 mole of each of these substances. We're assuming they're all in the same volume. So here, it's probably best if we just look at weight, that hydrogen is actually going to have the least entropy. Then it's going to be HCl because it's heavier, then HClO, and then the heaviest one. Or you can think O has more bonds too. Okay, the things that can bounce and wiggle are going to have a lot more entropy. But for the most part, this one's weight. The next one, it looks like the difference between all these substances, again, we're assuming all the same amount, is just the phases. So it's going to be solid, liquid, then gas, since it's all the same substance, but really what's changing is the phase. And the last one, this is tricky. I think I gave this on the exam and it didn't do well. Maybe. So here we have bromine gas, krypton gas, and bromine liquid. There's one off the bat that you can estimate, is the lowest, and that is going to be the liquid. Do you see why? It's a liquid. But the other two, the gases, we need to be a little bit more careful there. So I'm going to look at weight. Where my periodic table? Okay, bromine. So it's diatomic bromine. So this is about 800. And then krypton is 80, like about 80. So here we see bromine a lot heavier and actually more complex. So I think it's going to be krypton is next, and the most entropy is going to be that bromine gas. So it's heaviest and it's more complex. If we had an example of two molecules that had very similar molar masses, let's say chlorine gas and, or actually, no, I'm going to do this one. I'm going to say fluorine gas and argon gas. Both of them are gases. If you look up their molar masses, fluorine is about 38 grams per mole and argon is about 40 grams per mole. Those molar masses, they're basically identical, all right? They're basically the same mass. Which one do you think has more entropy, fluorine or argon? Fluorine, because it can bounce and wiggle. Yes, and vibrate when it's bouncing around the container. They both weigh essentially the same. They're so close. All right. These are more common on the exam, just predicting the sign of the following reactions. So we have to check both sides. So the first one, we're going from free ions to a solid. So entropy, the sign of entropy is negative, yes, of the reaction. Okay, taking a solid and turning it into a solid and a gas. Delta S is positive because we're forming a mole of gas. There's no gas on the reactant side. C, we are turning 3 gases into 2 liquids. Entropy is decreasing. I love these. And then, oh, that's it. Okay, all right. All right, that's what we did last week. Yeah, okay. So let's look at this one. So enthalpy of vaporization of mercury has this delta H, and the entropy of vaporization is this value. So it looks like I gave you delta H of your reaction and delta S of your reaction. So this is 59.11 kilojoules per mole, and then delta S of your reaction is 92 joule mole Kelvin. So that was what's given. I always like to organize the data because oftentimes this is how I got through physics. Is you write what's given to you, you look at your equation sheet and you ask yourself which equation has these things and the thing I want. And then you just figure out the pathway to get to that answer. So here I'm asking, what is the boiling point temperature of mercury in Celsius? So when does mercury boil? So recognize that boiling is turning a liquid to a gas. At the boiling point temperature, this reaction is at equilibrium. And we said this before, when a reaction is at equilibrium, delta G equals 0. So we're going to utilize the equation delta G equals delta H minus T delta S. And we're going to figure out at what temperature is this reaction equal to delta G equal to 0, given the other thermodynamic data. So if you organize this, you get that temperature, because it's equal to 0, is delta H over delta S. Perfect, and that was given. So it looks like we're just dividing these numbers. So to get temperature, just do I divide 59 by 92? Nope, you got to convert something. So I'm going to do 59 kilojoules over 0.0929 kilojoules per Kelvin. And you get some answer. I wrote this down. Let me drink my LaCroix. Okay. What page am I on? Let's see. I get temperature is 636 Kelvin, but is that what the question asked? No, it asked for Celsius. So make sure you convert it to Celsius, subtract 273, and you get something like 363 degrees Celsius. If this was a multiple choice question and I gave options 636 and 363, yeah, a lot of people would pick the other one. Or if it was numerical input, a lot of people who would get it wrong would put 636 because they just go, oh, temperature, but do make sure that you're reporting it the way that it wants it. Okay, I like questions like this. Without doing any calculations or looking up anything, consider this combustion reaction and choose the most correct statement. This reaction is spontaneous at high, low, all, or no temperatures. But I don't give you anything. So can you not figure it out? Nope, you guys are smart. You can figure it out. So in order to predict spontaneity, we need to predict what are the signs of delta H and delta S of this reaction. Got to think your way through it. Got to put more wrinkles on your brain. All right, delta H of this reaction, what do we think it is? What's the hint? It is combustion. So it is what kind of reaction? Exothermic, it is negative. All right, you're burning something. So it's negative. Okay, then the entropy change for this reaction, what do we think? We're going from 6 moles of gas to 7 moles of gas. So entropy is increasing. Okay. Now, we're going to use the equation that relates delta H and delta S to delta G. So delta G equals delta H minus T delta S. We're going to input those signs and ask ourselves, at what temperature is delta G come out negative? And I literally like to draw it. When T is small, what is the sign of delta G? It is negative, yes. But when T is really, really big, is also negative. So this reaction is spontaneous at all temperatures. Very good. It's always negative. It's always negative. Perfect. All right. Okay, let's do this one. Yeah, so this is more mathy. Okay. Ooh, thermite. Yes, thermite. Used for welding metal parts in railways and metal refining. Here's the reaction for thermite. So let's calculate delta H and delta S for this reaction. So we are simply going to do products minus reactants. So this is kind of tricky here. So we got, here are my reactants. In pink, I have my products. So just make sure that you choose the right things. So here is one of my products, and iron is another product. And then my reactant is aluminum solid and rust. So I'm going to take the pink ones and subtract the yellow ones. Make sure you take into account stoichiometry. It's 2 iron atoms and 2 aluminum atoms. But for delta H, that doesn't really matter because those values are 0. So for delta H of this reaction, it's the aluminum oxide, so negative 1669.8 kilojoules minus, and again, because iron and aluminum have 0 enthalpy values, then we're going to subtract the rust value, so negative 822.16, and that equals something. Okay, that's some value. All right, then we get delta S of our reaction. We do actually have to subtract and add all those numbers. And again, make sure you consider stoichiometry. For our products, it's all the pink ones. So there's 1 unit of aluminum, but 2 of iron, so 27.15. And then we're going to subtract all of the reactants. So 1 iron, 89.96 plus 2 aluminum. So 2 times 28.32. And then we get 2 answers there. What is it? Careful with your units. So here, delta H is negative 847.64 kilojoules. And then negative 41.3 joule Kelvin for entropy. All right. In this one, if you look at the reaction, this one's really hard to predict whether entropy is positive or negative. Usually in questions, we try to make it pretty obvious, but this one's hard. There's 3 solids on this side. There's 3 solids on that side. To me, it's not super obvious which one has more entropy, FYI. But we can calculate it. It went down. All right. All right, assuming delta H and delta S don't change with temperature, let's determine, can we do the thermite reaction in Antarctica? Let's go build a submarine in Antarctica and use thermite as our welding technique. You want to do that? But let's make sure with our team that it is even thermodynamically feasible to even do that. Because remember, reactions, their spontaneity changes depending on the temperature. And in Antarctica, it's a really crazy different temperature. It's negative, 57 degrees Celsius, which is also the same as, what did I say? What did I say in my key? 216 Kelvin. So our strategy here is we actually already have delta H and delta S from the previous question. All right, we got that delta H is equal to something. What did we say it was? Negative 847 kilojoules, and delta S was, it's right there, negative 41 joule Kelvin. So what we're going to do is use the equation delta G equals delta H minus T delta S. There's a couple ways you can do this. You can solve for T, and figure out, okay, when does this reaction not become spontaneous, and go ahead with it. Or you can just plug in that temperature and those numbers and see what kind of delta G pops out at the end. So negative 8,847 kilojoules minus that temperature in Antarctica, 216 Kelvin, times negative, again, this has to be in a kilojoule value, so 0.041 joule Kelvin. And I think if you do that math, you see that, okay, the delta G that comes out is still really negative. It's negative 838 kilojoules. It is still spontaneous even in Antarctica. But your boss will be very impressed with you if you just make a side note of it. If they're like, should we be worried about the temperature, in Antarctica and this technique that we're using? And you go, oh no, look at this calculation. It's still spontaneous at this temperature given thermodynamic values. And then you sound really smart. Okay. Okay. And then, so we'll do it again, assuming delta H and delta S don't change with temperature. So same thing, let's figure out at what temperature does this reaction begin to not be spontaneous. So here, yes, we are actually just going to set delta G equals delta H minus T delta S equal to 0 and figure out when does this reaction not become spontaneous. So temperature is delta H over delta S. Plug in those numbers, negative 847 kilojoules over negative 0.041. So that's kilojoules per Kelvin. And so you get the temperature where delta G is 0. So the separation between positive and negative numbers is 20500 Kelvin. All right, so temperature is actually above this point. This reaction is not spontaneous. So I know it's above because if you look at the signs of this reaction of the thermodynamic data, we see, if we increase temperature a lot, we're subtracting a negative number, and that's how the reaction becomes non-spontaneous. That's how delta G becomes positive when T is a really big number, right? And so it's above this temperature. So what's the temperature on the sun? Real hot. Let's see, can we do thermite welding on the sun? Temp, sun. Oh no, that temperature of sun. Oh, the sun is actually only about 5,000 Kelvin. So we can still do the thermite reaction on the sun. Fantastic. Okay, great. All right. So, all right. So we did all of chapter 10. Now what? It's been less than 30 minutes. What are we going to do? 8. Okay, let's do 8. 8 has no math. Yikes. So let's go over the trends. Okay, what are the trends? As your IMFs in your sample increase, what should you observe? I love intermolecular forces. It's an example where structure describes properties that we see. Me and my husband, we were watching, I'm like really into Martha Stewart Living right now because we got rid of cable. And I like to watch the Food Network, but we only get cable during football season. So I watch a lot of Martha Stewart Home Living. And she's really like gangster. This was pre-prison Martha. She's pretty cool. And she was showing how to like make toolboxes and stuff for your home, for like home projects. And she said something like, you know, one of those leveler things, right, with the little like bubble ball or whatever in it. So she had someone come in explaining all the parts and pieces to their little toolbox thing. It's cute. And he said like, oh, here's your leveler. It's made, it's filled with mineral spirits on the inside of the little leveler thing with the bubble. And me and my husband were just like, why is it alcohol? Why is it mineral spirits? Why don't they just use water? And then we just kind of like sat on it, never like answered it. But then I started teaching this chapter and then I realized why. All right. It's because if we think about mineral spirits smell really bad. Okay. Spirits, they smell really bad. So what does that mean about their vapor pressure? It's really high. So that means that they have what kind of IMFs? Weak IMFs. And so the question is, well, why do they use mineral spirits versus water? Because it would make more sense for them to just have water in those little leveler things. So if you think about water does not smell like anything. So at room temperature, it has a very low vapor pressure. So therefore, it has very high intermolecular forces. And so where I'm getting at is surface tension, because surface tension is also something that we discussed as a trend in this class. So what is the trend? As intermolecular forces, attractions increase in a sample, what do we see about surface tension? It increases. Things with high intermolecular forces have strong surface tension. Water has very strong surface tension. That's why when you see a leaf go on like the water, it like stays there because there's strong surface tension preventing that leaf from falling down. So that means mineral spirits have very low surface tension. Okay, so what's the moral of the story? Why are those little leveler things filled with mineral spirits? It's because they get banged around all the time on a construction site. If they get banged around, then it forms, that one bubble becomes many bubbles. And is that leveler effective if there's just a ton of little bubbles inside of it? No, you want one nice big fat bubble. And you can achieve that if the surface tension of the liquid inside of it's really low, meaning that you can shake the thing around and all the bubbles will coalesce with one another to one bubble. But if it's water has a really high surface tension. And so you might see 2, 3, 4 bubbles just kind of all sitting next to one another and not coalesced into one bubble. Right. And so then I like got really excited and told my husband, he's like, oh yeah, that makes sense. So I got it approved by at least one other person. So that's why I think it's mineral spirits. Unfortunately, Martha did not explain why, but I thought about the why. So, okay. So those are the trends, just some of them. And so the total trends is as IMFs increase, typically what we see is boiling point temperature increases. Vapor pressure of your sample. Oh, what am I trying to do? Typically decreases. Or you can think volatility of your things decrease too. Things that are volatile have very low intermolecular forces. So like I'll just say low volatility. Okay. Mineral spirits has very high volatility. Water has very low volatility. Okay, so that's, what else did we talk about? Surface tension, that increases. What else? Viscosity increases, things flow slower. Okay. Delta H of vaporization also increases, so the energy to turn something from a liquid to a gas. And then some side notes about vapor pressure. Yes, as you change your substance, right? You change your substance, you change the magnitude of intermolecular forces, but we can also change vapor pressure by changing temperature. So as temperature increases, we also see vapor pressure increase, right? You stick a cup of vinegar in the microwave and pull it back out. It gets smellier because the heat, the added kinetic energy increases that vapor pressure until it boils. Viscosity. If you increase the temperature of something, how is its flow rate change? It actually decreases. Yes, that's why you warm up your car before doing an oil change, emptying your filters. I need an oil change real bad, but I'm lazy and it's real cold. Okay, so those are the trends. So really what all these questions do is they ask, which one has the higher normal boiling point temperature? So really it's asking which one has higher IMFs. That's all it's asking. All of these questions come back to IMFs. So if you look at these substances, the first one, the strongest IMF that's affecting this first one, yes, it has London dispersion forces. Yes, these are polar molecules, but what's strongest and most important is it has these NH groups on them. NH can do what? Hydrogen bond. Yeah, so hydrogen bonding is kind of this very special polar molecule case where if you have a compound with an OH group or an NH group, it can participate in hydrogen bonding and has exceedingly strong IMFs. So which one has stronger IMFs, the first or the second one? The second one, because it has two really strong hydrogen bonds, right? The second one, Br2 or ICl, it's going to be the polar one that it has more IMFs, has the higher boiling point temperature. How did I know ICl is polar? I didn't even draw it. The what? Not quite. I know that it's polar because the two atoms are different. That's it. I and Cl. I just know that they will have different electronegativities. Two dots always make a line. So if the two atoms are different, they're going to pull on each other differently. Versus bromine, the two atoms are the exact same. So that's going to be a nonpolar molecule. That makes sense? Yeah. Okay. So the two atoms are different. All right. pH3 or ASH3. Here, if you draw them out, you see, oh, they are both polar molecules. So the factor we're going to look at here, they're both a trigonal pyramid. The factor we're going to look at is weight because they have the same polarity. That's not really we can't really see a major difference here. So we can look at weight and we see that the arsenic containing compound is much heavier. So here we're looking at molar mass because we're assuming that their polarities are the same. They're shaped the same. All right. So I could change this question. How could I change this question? If I said so I said higher normal boiling point temperature. How about if I said viscosity? How should I change this question if I wanted all the answers to stay the same? Would I be asking which one has the highest viscosity or the lowest viscosity? Highest viscosity, yeah. So those are just all ways to ask the same question. Because look at this one. Which one exerts the highest vapor pressure at room temperature? So what am I actually asking? Which one has the least IMFs? So same strategy. CCl4, CBr4. What factor should we look at? Weight. Yeah, so CCl4 is lighter. They're both nonpolar. This thing with a lot of carbons and hydrogens, or this thing with a lot of carbons and hydrogens, but there's a chlorine tacked on the end. The first one, yeah. Because the first one has what kind of polarity? Nonpolar. It's all carbons and hydrogens. But the second one, how do you know it's polar? That chlorine, it just being present there is going to make it polar. All right. It's disrupting all that symmetry. You don't really have to draw it out just because it's there. It's going to make the molecule polar. Or H2O or H2S? Which one? This one's tricky because both of them are polar molecules. Yes, it's going to be H2S. And the reason is that water can hydrogen bond and this one can't. Both of them are polar though. Okay, so water is one of those exceptional cases that, yeah, it's a really light particle, molecule, but it has exceedingly high IMFs. We're lucky we live on Earth. Okay. Okay, based upon these normal boiling point temperatures, which one is the most viscous? So remember what boiling point temperature tells us. As boiling point temperature increases, what happens to IMFs? It also increases. So what happens to viscosity? Also increases. So of these, which one has the highest IMFs? The C one, yep, because that's the highest boiling point. So therefore, that one's going to be the most viscous. Okay, so that one just kind of, we had to use all the relationships to get there. All right, this one. Which substance, based upon their vapor pressures at room temperature, will have the highest boiling point temperature? So these are the vapor pressures measured at room temperature. So if I had solutions A, B, and C all sitting right here, A would exert 50 torr of gas. This one, this B would exert 30. This one would exert 20. So you can kind of think the same thing, right? As IMFs increase, vapor pressure decreases. But as IMFs increase, typically what we see is boiling point temperature increase. So we are looking for which compound? The one with the lowest vapor pressure. Or I like to think of it this way. A sample will boil on Earth when its vapor pressure equals 760 torr. A is already close to boiling already. So this one has the least IMFs. It's going to be basically already at its boiling point already. So it's the other one. You got to heat this one a lot higher to get it to 760 torr, to get it to boil on Earth. All right. Yes. All right. So let's keep going. All right. Which substance will exert the highest vapor pressure at the respective normal boiling points that are given? This one's a trick question. A sample will always boil on Earth when? When its vapor pressure equals 760 torr. So I'm asking you which one exerts the highest vapor pressure at these boiling point temperatures. So when water boils at 100 degrees Celsius, what is its vapor pressure on Earth? 760. What about ethanol? What is its vapor pressure at 78 degrees Celsius? 760. All of these are 760 torr. All of them actually exert the same pressure at their respective boiling point temperatures, because any sample will boil when it equals external pressure. Remember the demo I did of boiling water at room temperature? It was literally cold water. I was able to achieve that by reducing the pressure around it. So I was able to change that external pressure. Instead of it being the regular 760 torr, I was able to reduce it down to like 50 torr. So it would boil. Because that's how, when a sample boils, whenever its vapor pressure equals external pressure. So that's why in Denver, water boils easier. So at a lower temperature, because it doesn't need to get as high to boil, versus in a pressure cooker, water boils at a higher temperature because you've added a lot of pressure. I like the pressure cooker I have because you literally put a weight on the top and you can see the pressure trying to, push that weight up. And so you have to heat the water more to get the gas to push away the weight and the regular atmosphere that's around. Right? And so that's how a pressure cooker works. Okay. Which statement is false about viscosity? Viscosity increases as temperature decreases. Is that true or false? False? Wait. Think about maple syrup. Hot maple syrup flows fast, right? Yeah. And then cold maple syrup is all slow. So this one is actually true. Because less temperature, less kinetic energy. Okay. Viscosity increases as molecular weight increases. Yeah, that one's true too, because here molecular weight increases, your IMF is probably increasing, so your viscosity can increase. Viscosity increases as intermolecular forces decrease. That's the false one. Yes. As attractions increase, viscosity increases. I like to think of it as like you pour something out of a container, all right? Your liquid, all those particles, they're holding on to one another, right? And if there's a really strong attraction between all those liquid particles when you're pouring it out, if it's really strong, it's going to pour out really slowly because they don't want their friends to leave them. They want to hold on real tight to their friends, versus they're really weak attractions, they'll just let their friends go. They don't care, right? And then it'll flow really fast. Yeah, okay. Okay. All right, so that's half the chapters. I was thinking a loser to make the looser, make the level more sensitive to angle. Oh, a lower. Okay, yeah. Okay. I was thinking a lower surface tension would make the leveler more sensitive to angle changes. That's true too. So the leveler, okay, we're going back to the leveler, all right? Right? Yeah, so if you know you got your bubble, right? I think that's a good point too. I was just thinking about like practicality and like, you know, bubbles forming, but I think in the end it comes down to surface tension too. If you have your little leveler and if there's high surface tension, if this was like water is here, this is your bubble. If there's high surface tension, there's high attractions to the glass. And so if you make small changes, then that water droplet might just like stick to the glass and not move. Actually, that's a really great point too. I like yours actually better than mine. Versus I was saying, oh, if it's water and there's really high surface tension, you know, if you knock your leveler around and there's like a bunch of bubbles in here, like now it's not even useful. Yeah, I like yours better. That's why you guys are engineers. I guess I just don't use levelers enough. Okay. I got a really big one, leveler, but I never use it. Same thing with that tape measure I walked around and showed everyone. I never use that big. It's so heavy and big. I actually like my really little one. It's just easier to like get around and put in my pocket. Okay. All right. Anyway. All right. Okay. What chapter? Well, we're like not even an hour in. We're going to just finish. We're just going to finish this. Okay. We're just going to go in order. Okay. We're going to do 9. All right. Assign Q and W of the system for these processes. So do you matter? No, you don't matter. So the reaction absorbs heat. So what is Q? It is positive. So what do you feel when you hold the reaction in your hands? It feels cold. But Q of the reaction is positive. Isn't that weird? Wouldn't you agree that that's kind of weird? It is weird. Okay. And expands against an external pressure. So here, I think the best way to recognize work, chemists don't do work very well. We're typically talking about like expansion and contraction of gases. So I would just memorize this equation. I'm not sure if I give it to you. Work of your system equals negative pressure, external pressure applied, times delta V. So that means when your gas sample contracts, delta V is negative, so work is positive. When your gas sample expands, delta V is positive, so work is negative. Your system is negative. Okay. Is it work on the system or by the system? So it depends on the sign. So if work, this is, okay, so let's go back to Q. When Q of the system is positive, it means that the system gained heat. When Q of, so in this one, Q of your system is negative, your reaction, your system is losing heat. It's giving off heat. So it's kind of the same thing for work. It's just weird. So I like to think of it this way. If work of your system is positive, the surroundings put work into the system, meaning it's squeezed on your sample. And that's how you get a negative value, or sorry, a negative value of delta V. And then since all of this is negative, then a positive value comes out. So a positive value of work means that you, the surrounding, squeezed on your sample and made it smaller. Versus when work of your system, when your system does work, I like to think your system is putting work out into the world. It's releasing it. So that's why work is negative when your sample expands. Or just memorize the equation. Did I give you the equation? Can someone check? Or let's check. I did not. So just memorize it. All right. I like to think of why I look at this equation, I think, why are diesel engines like better in terms of like torque and power? And it might be because, or, maybe not diesel engines, but like engines that use premium gasoline, they typically have they operate at higher pressures. They're able to compress the gases more. And so you should be able to get more work out of the system. If delta V is a larger value, if pressure is a larger value here, then you should be able to extract more work out of a car that runs off of premium because they have higher compression values in their engine. Except my dad, he's convinced that Lexus and Toyota engines are the exact same on his Toyota Sienna and my Lexus RX. And he keeps saying that it can just take regular just fine. But on the thing, it says premium only. I hate my car so much. It is a gas guzzler. Okay. All right. So there's cars. All right. Let's keep going. Oh, we didn't even answer this question. So if your sample expands, what is the sign of delta V? Positive. So therefore, there's a seat right up here. Hang out with me up here. So if delta V is positive, then that means work of your system is negative. All right. So just memorize the equation. Okay. Reaction loses heat and contracts due to external pressure. So delta V is negative. Therefore, work is positive. Keep going. Okay, reaction is endothermic. So Q of your reaction is positive. The reaction gains heat. You hold it, it feels cold. Versus an exothermic reaction, you hold it, the reaction loses heat. It feels hot. Feels hot. Contracts, so that means work is positive. The one that expands, work is negative. All right, so I think with the work one, it's definitely a tricky one. I would just memorize the relationship between how the gas sample expands and contracts, and relate that to the sign of work, because that one's definitely less intuitive. Okay. All right, let's look at this reaction. What is the delta H of this reaction? So enthalpy, like entropy and Gibbs free energy, these are state functions, meaning that if you manipulate the reaction in any way, if you flip it, double it, whatever, you do the same thing to that thermodynamic value also. So look at this reaction and ask yourself, how did you manipulate it? What do I have to do to make them match? The reaction, it looks like I flipped it. And then what else did I do to it? You divided it by 2, so times a half. So how do these two delta H's relate? You multiply the original delta H by a factor of -1/2. And that's how you get the new delta H, right? Negative because I flipped the reaction, times a half because I divided the reaction by 2. Do I need to show each step there? No? Okay. All right, so putting that together, oh, nope, that was just it. All right, let's calculate the amount of heat that is released when 25 grams of HCl is produced by this reaction. So I kind of combined these two questions. I'm gonna erase this real quick. Here is the thermochemical equation, the relationship between, reactants, products, and energy. So if I wanted to determine, if this was chapter 3, remember chapter 3 and 4, such a simpler time. We used to say, 1 mole of H2 is equal to 2 moles of HCl. That's stoichiometry. We were able to make relationships. If I knew how many moles of HCl I wanted, I could calculate via stoichiometry how many moles of hydrogen I needed to add. So it's the same thing here. But instead of working with, reactants and products, I can make a relationship between any of the substances and energy. So I can say here that for every 2 moles of HCl this reaction uses or, makes is equal to -186 kilojoules. So I'm just treating delta H like a component of this reaction, a new way to use stoichiometry. So if I start with 25 grams of HCl, I can use the molar mass to convert to moles, so then I can use the stoichiometry. Oh, we haven't done a molar mass in a long time. So molar mass of HCl is 36. Where does the 36 go? On the top or the bottom? On the bottom. Yes, so 36.46 grams on the bottom is 1 mole of HCl. So I just determined how many moles of HCl I want to make. If this was chapter 4, you could go to moles of H2 and then grams of O2 or H2. If you wanted to, if that was chapter 4, but this isn't. We're going to delta H of the reaction instead, but it's really no different. This reaction releases negative 186 kilojoules of energy, but what value goes on the bottom? 2 moles of HCl. Yeah, so for every 2 moles of HCl, you make that much energy, and then your answer is there. So really, this is the new part, but it's not really that new at all. Okay, so let's write the thermochemical equation for the standard enthalpy of formation of iron 3 chloride. So yes, you can look up in the textbook the formation value of iron 3 chloride, but that number represents a reaction. So do you know what reaction it represents? So to write a formation reaction, you take the thing, you make it the product. Make it the product. And then you ask yourself, what elements do you need to combine to make 1 mole of that thing? So formation values is the energy to make 1 mole of your thing from elements in their most stable state. So we go through all of the elements here and recognize, okay, we need an iron. Iron in its most stable state in the elemental form is iron solid. Now you need chlorine. And so it's a 1-to-1 ratio, so you're good. Now we need chlorine. Chlorine is what in its most stable state? A gas, but is it just chlorine atom? It's not. It's one of these 7 diatomic. So it's chlorine 2 gas. What do I need to put as my coefficient in front of chlorine? 3/2. Should I multiply everything by 2 to get rid of the fraction? No, you shouldn't. Because formation values are in the unit of kilojoules per mole. And so our goal is to make 1 mole of this. And if that requires 1/2 mole of something, that's fine, because we need to make just 1 mole of this, right? So no, we don't. We leave it as is. So it means that this reaction, when you look it up in the table value, this reaction has a delta H of formation. This reaction is negative 826 kilojoules. That's what that means. Right. So, some questions are from students is like, okay, why is O2 gas not have why do I not give you a formation value for oxygen gas? You need to know that oxygen gas has what formation value? It's 0, and this is why. Try to make the formation reaction for oxygen gas. How can you make oxygen gas from elements in its most stable state? What's the reactant? It's just O2 gas. So how much energy does it take me to go from that to that? 0. That's why elements in their most stable state have a enthalpy and Gibbs free energy formation value of 0. It's because it takes no energy. The things are already in their most stable state. So that's why those energy changes are 0. Okay. So given these delta H values, calculate the delta H of formation for iron 3 chloride. So here, usually when I have you do Hess's law and I ask you to manipulate reactions and put them together, usually I give you the target reaction. But did I give you the target reaction? No, but can you figure out what that target reaction is? It's the delta H of formation of iron chloride, which we got up here. This reaction that we did just earlier is my target reaction. All right. So we need to manipulate these equations to make sure we get our target reaction. Right? So I like to focus things on one at a time. So if you look here, notice how chlorine shows up in two places. I'm going to ignore that one. And I'm just going to pray that once I finish everything else, that the chlorines cancel out to the number I want. So I'm going to focus on reactions where what I want only shows up in one place. So here I see iron solid. And there's iron solid in my target reaction. So I ask myself, is it on the right side of my reaction? It is. It's a reactant. Is it in the right number? Yes. So I'm going to leave this reaction as is, completely as is. And I'm going to add it to the next reaction, but I need to see if I need to manipulate the second reaction. So I focus on what's in common. So I see there's iron 3 chloride. Is it on the right side? No. So I need to multiply by -1. Is it in the right number? No. So I have to do what? Divide by 2. Yes. So we can rewrite these equations. So I'll just do that real quick. So the reaction that's happening is iron solid, chlorine. I'm going to actually just drop states because I'm lazy. Goes to iron chloride. And then the second reaction, I'm flipping and dividing by 2 at the same time. Let's see, am I smart enough to do that? So I'm dividing by 2. So iron Cl2 plus half a chlorine. And then 2 divided by 2. So 1 iron chloride, iron 3 chloride. So if you add up these two reactions, you can check yourself. Did you get your target through your manipulations? And it looks like we did, because the iron with 2 chlorines canceled. We didn't want that one, but it cancels out perfectly. And then how many chlorine molecules add up here? This is 3/2 chlorine, and that's exactly what we want. We're left with iron chloride and that one over there. So yes, we can be satisfied that these two reactions add up to the target, and how we manipulate delta H is what we need. So it's -341.8, because we didn't manipulate the first reaction at all, but we changed the sign of the second one, and we need to divide by 2. So add up those two numbers and you'll get the delta H of that target reaction. And I think this one doesn't match the last one. I don't know. I think my numbers I put in are wrong or something, but it doesn't quite match the delta H formation value in the previous question. I don't know what I did wrong. Okay. So, oh, dang, we almost done with this one too. More conceptual things. Sort of. Okay. Okay. So this is calorimetry. Some of the hardest stuff in this chapter, very math intensive. But I always like to throw in some conceptual things that, you don't actually really have to do the math. You can kind of just compare some stuff. So we have 2 items. We have a 5-gram block of aluminum with this specific heat, and we have a 10-gram block of copper with this specific heat. All right. So based upon the specific heats, which substance resists temperature change more, aluminum or copper? Aluminum resists temperature change more. I'm trying to think of like an example, like aluminum foil, like you pull it out of the oven and it cools off rather quickly. Yeah, it comes hot out hot, but then it cools off. No, that's not actually a good. I can't think of a good example right now. But anyway, yes, aluminum has a higher specific heat. But here's the thing, this is specific heat. If I'm comparing the same amount of aluminum and copper, 1 gram and 1 gram, yes, aluminum heats up or changes its temperature slower. It takes more energy to get it to change its temperature. But that's if we only compare 1 gram and 1 gram, or the same masses, like 5 grams and 5 grams. We just compare specific heat. But here's the thing, are the objects the same size? No. So what we actually want to do is compare heat capacity. If I truly wanted to understand how do these objects differ, because these are unique objects. We can't just look at specific heat. We actually want to calculate heat capacity instead for these objects. So I'll point out that heat capacity, heat capacity is equal to specific heat of your object times the mass of your object, right? So I like to think of it this way, that the heat capacity is unique. Capacity is unique to your object, right? Specific heat is specific to the identity of your object. Like, is it copper, aluminum, gold, whatever. But then the mass is taking into account, oh, how big is your actual object, right? Your intuition knows that a cup of water versus a pool of water, which one heats up slower? A pool. Is it because the specific heats are different? No, it's because their heat capacities are different, okay? So, we can't always rely on specific heat for us to determine the difference in, behaviors of objects. Sometimes we have to take into consideration their masses as well. But sometimes I can force you to just look at specific heat if I make the objects the same size. But in this case, they're not. So if we calculate the heat capacity of both of these things, we can better compare them. All right. So I'm just going to multiply its mass times its heat capacity that's given here. So what is that? What is that? So if you do that, you get that aluminum has a heat capacity of 4.4 joule Kelvin. Copper has a heat capacity of 3.9 joule Kelvin. This object. All right. So if you deliver the same amount of heat to both of these objects, the copper one increases its temperature more, versus if you deliver the same amount of heat to 1 gram of copper and 1 gram of aluminum, oh wait, then copper also increases more. Yeah. Okay. So here's the thing, look at heat capacity for these specific objects, because I could simply change these numbers. It could be, 20 grams of copper or something, and then these heat capacities would change. So let's look at these conceptual questions. True or false? Aluminum has a larger specific heat than copper. That is true. These are the specific heats, 0.88, 0.39. Yes, aluminum has a larger one. The heat capacity of 5 grams of aluminum is greater than the heat capacity of 10 grams of copper. That is also true. We just calculated it. Remember, heat capacity takes into account the mass of your thing as well. And then I'll tell you a story after this. 10 grams of copper is more resistant to temperature change than 5 grams of aluminum. True or false? What do we think? Nope, it is false, because what are we comparing? Are we comparing specific heats? Nope, we're comparing the heat capacities here. That aluminum, oh wait, hold on. Yeah, where aluminum is more resistant, it requires more heat to get that to change temperature than copper. Okay, 10 grams of copper. I should have made the numbers better where the heat capacities flipped it. Should have done that, but oh well. 10 grams of copper can deliver more heat to a small cup of water than 5 grams of aluminum. Which object holds more heat? Look at the heat capacities. It's actually the aluminum can hold more heat because it has a higher heat capacity. So this one is false also. Again, because of heat capacity. So which ones are about capacity? This one's capacity, this one's capacity, this one's capacity, all because we had to incorporate the masses. The first one is just about specific heat. So we don't need to consider capacities. It's just asking, just compare a gram to a gram. But these ones, the subsequent ones, actually have to do with masses. 1 gram of aluminum will deliver more heat to a cup of water than 1 gram of copper. Do I look at heat capacities for this one? No, you look at specific heats because it's a gram to gram. Look at the unit of specific heats, joule per gram degrees Celsius. It's how much heat is required to raise 1 gram of substance 1 degree Celsius. So here you're simply just looking at specific heats. So this one is true because the specific heat of aluminum is greater. And then finally, 1 gram of aluminum is more resistant to temperature change than 1 gram of copper. That is also true. Again, these last two are simply specific heats that you're comparing. Okay, so let me tell you my story. So, you all cook and stuff? Yeah, okay. So when you cook on the stove, usually what heats up faster? Oil or water? Oil. Yeah, you were really quick on that. So if oil heats up a lot quicker, its specific heat is probably what versus water? It's probably lower. Yes, very good. Specific heat. Okay, so here's the story. Every Thanksgiving, I deep fry turkey. And so I give it to my husband and my father-in-law to go on turkey duty. I prep everything. I have all the oil out. They just have to set it up. Okay. One Thanksgiving, it was like 10 degrees Fahrenheit outside. It was so cold. And I had a plan, right? Cooking is not just about like cooking and like executing it well and like cooking it so it tastes good. It's all about timing, right? I'm at the point in my life where it's like, I need to make sure all the food is hot all at the same time, right? They all finish at the same time. Everyone has hot plates and everyone's enjoying every single bite for like the entire meal, right? So that's me. So I'm all about timing. I wanted the turkey to drop at like 11 a.m. We're early Thanksgiving people. I don't know about you. I'm an early Thanksgiving person. I wanted the turkey to drop at 11. No, or like 11:30. I wanted it to drop at 11:30. So I told my husband, drop it at 11:15, you know, to give him some buffer time. Because I knew it would only take the turkey maybe like 30 minutes to cook and then like another 20 minutes to rest before carving it. Okay. So, and then we'd eat by like 12:30. That's exactly what I wanted. So that means they need to drop the turkey, you know, at 11:30. And so it's like 10:30 in the morning. They still haven't taken out the turkey fryer, right? That the like oil is still like sitting by the front door because they're going to bring it outside. It's 10:30. They haven't set it up. And I'm like, you know, crazy with my head cut off and they haven't set it up. Again, it's like 10 degrees outside. And I'm like, why have you not set it up? And then my father-in-law said something like, oh, it's oil, honey. It's not going to take that long. Right? Because that's what kind of our intuition says, that oil has a fairly low specific heat. But think about it. When you cook on the stove at home with a little bit of oil, do you use a lot? No. Do you know how many gallons of peanut oil I have to get for to deep fry a turkey? It's like 10 gallons. I only use about 8 of it, 8 gallons. Okay. So when they go out there to start the thing, they're finally like, oh, okay, I guess we'll do it. Like 10:45. They go at it for like 30 minutes and the heat, like the temperature of the oil barely moved. Because the difference is here that yes, oil has a fairly low specific heat, but when you're trying to heat up 8 gallons of it, that's a very large what? Heat capacity that you still have to deliver tons of BTUs in order to get that temperature to go up. So we didn't drop that turkey until like 12. And I think we didn't even get it to like the 375 it was supposed to get to. It was like the temperature, I think, in the oil was like 325. And I'm like, just do it. But here's the thing, it was the best freaking turkey we ever had. It was the best. Like that year I made a brisket, a smoked brisket and a turkey. No one ate the brisket. And every year they eat the brisket, but this year everyone ate that turkey. It was so good. It was so good. But it took like a very, very long time to heat that oil. And because I think my father-in-law got stuck in that misconception that, oh, it's oil has a low specific heat. But actually what we're comparing is heat capacity, right? 5 gallons of oil is a lot of oil, right? Who else fries a turkey? No one else fries a turkey? What? You do a brisket? What kind of brisket? Do you smoke it or? Okay, yeah. Oh, coffee rub. Okay. No, I just wrap it. I have to start it the day before. I thought frying turkey was dangerous. It is dangerous, and we use multiple precautions to prevent issues. And the biggest issue is ensuring that your turkey is completely defrosted. I always cook small turkeys. There's it's an American thought that bigger is better. But when it comes to turkeys, that's not the case. Because the smaller the turkey, the faster it cooks. So you can ensure that the outside and the inside are both cooked, versus if it's really big, you have to cook it forever and it's so dry. But yeah, the problem is if you put it in partially frozen, it explodes. Yeah. So, but we have precautions. We do it outside. It's all good. We put a fire extinguisher out there. Yeah, just in case. All right. Okay, let's keep going. All right, let's do the hardest question of the exam. Here's the thing. This question. This is lots of places to make mistakes. It's going to take a lot of time. I suggest to everyone in this room, if you run into this question on the exam early on, just skip it and come back to it later, because it's going to take you a long time unless you're really good at them, and you're still probably going to get it wrong. So I don't want you to waste time on a question that you're still going to get wrong. So this question, though, is very systematic. I'm just saying there's a lot of little places to go wrong, all right? And I don't want you to spend like more than 5 minutes on this question, all right? So we are dissolving calcium chloride in water. The temperature of the water goes up. What is delta H of this dissolution reaction? That's what this is asking, right? So delta H of your reaction is equal to Q of your reaction over the number of moles of stuff that you dissolved. So we need to figure out how much heat was involved in this reaction. So this is calorimetry, where we utilize the first law of thermodynamics, that the heat lost somewhere is always gained somewhere else. Always. So the best thing to do with this dissolution process is say, oh, the heat lost by this reaction is gained by your solution. Think about what you're putting in that cup. You got 120 grams of water, but also you have 6.23 grams of salt. All of this increases temperature. It increases from 21 to 30 degrees Celsius, all right? Without even doing any calculations, tell me, what should the sign of delta H of the reaction be? What should it be? If the temperature of the water goes up, the reaction did what? Lost energy. Yeah, so it is a negative sign. Delta H needs to be negative. I tell the story in class. I did this exam in 7 minutes, and I only got one question wrong. And which one was it? It was this one. And why did I get it wrong? It was just a negative sign. Did all the math right. It was just a negative sign. Okay, so even before attempting the question, just get the sign right. Get the sign right. We should expect this is an exothermic reaction. You put the salt in water, it dissolved, it releases heat, just like a combustion reaction does. Right? So we're gonna utilize this equation. Okay, we can't measure Q reaction directly, but we can measure Q changes for the solution. All right, my thermometer is sitting in this solution, where Q of solution, that solution has a mass. It has a specific heat. It has a delta T that we solved or that we observed. Delta T is always final minus initial. So 30.2 minus 21.6. I think that is equal to something. Is equal to 8.6. So this solution gained 8.6 degrees Celsius. Specific heat of the solution is same as water. So 4.184 joule gram Kelvin. Mass of solution is what? 126. Yes, it is not 120. That's the common mistake students make. They go, oh, the water heats up. Nope, everything in the cup heats up. So that includes the water and the mass of the salt. So the mass of the solution is actually 126.23 grams. Right? We're going to Q equals MCAT the solution and relate that back to the reaction. So Q of your reaction is equal to mass of your solution times specific heat of your solution times delta T of your solution. Those are all things we know and measured. So negative Q of your reaction is equal to 126.23 times 4.184 times delta T, so 8.6 degrees Celsius. So we see that that solution gained 4,542 joules of energy, the solution. But that means, where did it come from? It came from the reaction, right? So that means the reaction lost that amount of energy. So Q reaction is actually negative 4.542 kilojoules. I'm going to convert it to kilojoules because we need that for the next step, right? The reaction lost this amount of energy. That's consistent with what you know, okay? But the solution of the water went up, it released energy. Q reaction should be negative. That's what we care about. We don't care about the water. We care about the reaction. So the last step, this actually isn't our answer, is calculating delta H. We take that number because this number just represents how much 6 grams of salt releases. Okay. You know, textbook authors don't care about that. They don't care about how much 6.23 grams of salt, how much heat it makes. We care about how much per mole do all of these salts make. Because if we report it in a per mole basis, I can compare your book, your value to your value to your value. Because if you use different masses, as long as you convert them all to the same kilojoule per mole unit, we can compare them side by side. So that's why we convert it to delta H in kilojoules per mole to scale it up so we can compare it to one another. So this value is that negative 4.542 kilojoules over the moles of salt that we used. So 6.23 grams, but we need to convert it to moles. So we're going to divide it by 110.98 grams, 1 mole. Right. So the denominator is just the mole amount of that salt. And that's what we get. And then hopefully we get a negative value. I think what comes out is negative 81 kilojoules per mole. So dissolving 1 mole of that salt will release 81 grams or 81 joules of energy. That's more useful to us than this Q value. That Q is specific to these experimental conditions. Okay, so let's keep going. Oh, and then we're done with this chapter too. Dang, okay. All right, so let's do this one. Using standard enthalpies. Calculate delta H's of these reactions. So I gave you 3 substances. We're going to do products minus reactants. But notice how some of these things, they have more than 3 things here. So here I give you rust is negative 826 kilojoules. 3, we're going to add that to 3 COs. So negative 110. Deep frying a turkey should be the next demo. It could be actually, because deep frying a small turkey only takes like 30 minutes. It's like 3.5 minutes per pound. So if you get a pretty small turkey, like it doesn't take any time at all. Yeah, that'd be cool. All right, so that is the sum of my reactants. Let's do the sum of the products. So CO2 is, we got 3 of them times negative 394. But where's iron? Did I not give you enough information? It's 0, yeah. So 2 times 0 is just 0. So don't let that fool you. And so what you get, sum up both sides. So negative 1156 on that side. This one is negative 1182. And so delta H of this reaction is products minus reactants. So negative 1182 minus negative 1156. And so we get that this reaction is negative 26 kilojoules. So it's a little bit exothermic, right? So same deal with the second one. We know CO, 2 times negative 110. What is the formation value for O2? I didn't give it to you, but you know it is 0 because it's an element in its most stable state already. But I give you CO2. It is a compound that you are given 2 times negative 394. Do products minus reactants, you get the delta H. You can do that with delta H. You can do that with delta G. You can do that with S. But note that S you do have entropy values for elements. Okay. So that is enthalpy. So I want to do one more. Let's do one side one. Okay. So I need my calculator. Let me just do some math. 100. Okay. Okay. All right. So you do the coffee cup calorimetry experiment. All right. And we want to calibrate this coffee cup. We want to calibrate that coffee cup. So let's do that by, oh crap, what did I do? Throwing a hot piece of metal into cold water. Okay, that's what we're gonna do. A hot piece of metal into cold water. So I'm gonna give you some numbers. And so we're calibrating this. So there is a theoretical maximum. If we know the initial temperature of our metal and the final temperature of our metal, we can figure out how much water, or sorry, if we know the initial temperature of our metal, we know the initial temperature of our cold water, we should be able to calculate what is the theoretical temperature heat transfer should happen. But when we measure it in lab, it's going to actually be a little bit different. So give me 1 second. 4 times 3. Okay. 5. Okay. So let's say you have a piece of metal. Its initial temperature is 80 degrees Celsius. All right. You have cold water. Its initial temperature is initially 10 degrees Celsius. Right? The piece of metal has a mass of, let's say, 25 grams. And let's say your water has a mass of 100 grams. Right? Let's say the metal is aluminum, so its specific heat is 0.88 joule gram degree Celsius. And let's say that the water, it's water, so you know that the specific heat is 4.184. All right. So we could calculate. This is all the information we need. We could do, okay, heat lost by something is gained by something else. So in this case, negative Q of the metal is equal to positive Q of the water. We could go ahead and calculate what is the final temperature for both of them, because both of them are going to share the same final temperature, right? So here's the thing. Let's say we actually do this experiment, but we get that the final temperature, okay, when we mix these two things, the final temperature that we get of the metal and water, let's say it is, hold on, 2 times. Let's say it is, I don't actually know if these numbers are going to work. 25 times. Let's say it's going to be 12 degrees Celsius. I don't know if these numbers are going to work. Let's just see if they work. All right. So that's my final temperature. I mix these two things, and then the final temperature of both of them is 12. Let's calculate what is the calorimeter constant for this system. Right. So we are going to utilize the first law of thermodynamics, so the same thing, and understand that we don't live in a perfect world. That cup may or may not absorb heat. So we're going to still say, oh, the heat lost by something is gained by something else. But the problem is it's not only being gained by the water. In the HCal experiment, we said, oh, heat was gained by the water and the cup. And that's what we're going to do and say here, that the heat lost which is from the metal, is equal to the heat gained by the water and by the calorimeter, the cup. Right? So here's the thing. There's two different Q equations we work with in calorimetry. Q equals MCAT, that uses specific heat. And then the other one is the one that uses heat capacity. So Q equals the calorimeter constant times delta T. So we're going to use a combination of these for all of these variables. And if you look at what information is given, this is how we can decide. Q equals MCAT. Use this if you know the mass of your object, your specific heat of your object, and the temperature change. But use CCal for something like your cup, because the mass of your cup doesn't change. We just want to get its calorimeter constant because its unique objectness doesn't change from experiment to experiment. So the metal and water, you're going to Q equals MCAT, but the cup, you're going to use CCal instead. So if we do that, let's get some information here. All right, delta T of your water. It started at 10, ended at 12. The delta T of the water is plus 2 degrees Celsius. Delta T of your metal is what? Final is 12. Initial is 80. So it looks like delta T of your metal is equal to, what is that? 68 degrees Celsius. Yeah, negative 68, sorry, negative 68. So this piece of metal lost 68 degrees Celsius of temperature. That's going to be useful because I don't want to bring out the TIs and TFs and stuff because all of them are actually measured. So I'm going to replace these Qs with our MCAT or CAT equations that we need. So Q of your metal is actually equal to mass of your metal, specific heat of your metal, delta T of your metal. Do we know all of those terms? Do we know how much the piece of metal weighs? We do. Do we know its specific heat? Yes. Do we know how much its temperature change? Yes, we know all those numbers. So Q of your water is mass of your water times specific heat of your water times delta T of your water. Do you know all those values? Do you know the mass of the water? Yep. Do you know the specific heat of the water? Yep. Do you know the temperature change of the water? Yep. So we do the last one, but don't Q equals MCAT the cup, because I don't know the mass of the cup. But what I do want to get is the heat capacity. So I'm actually going to Q cat it instead. So Q cup becomes CCal delta T of your water. We're going to assume that the cup makes the same temperature change as the water because that's those two objects are closely aligned with one another. And so what we see here is there's only one value we don't know, and that is CCal. We know every other piece of information here. So putting in these numbers, and I do hope that the number we get out is a significant number. Mass of your metal, I told you, is 25 grams. Specific heat of the metal is 0.88 joule, gram, Kelvin. Delta T of the metal is negative 68 degrees Celsius. So what you can do just right off the bat is recognize that, okay, how much energy did that piece of metal lose? It lost 1496 joules of energy. So it would make sense if the water gained that much energy, but we don't live in a perfect world. And sometimes what will happen is, the water will only gain 1300. So that means the cup had to gain the rest. And that's the purpose of calibrating your calorimeter. So let's actually get the actual numbers though. So here, let's plug in the waters for the piece of the metal, or sorry, if we did the metal, let's do the water. So the water is 100 grams. The specific heat of water is 4.184. Delta T was 2 degrees Celsius. So what is that value? Oh, let's see if this number makes sense. 100 times 4.18184 times 2. Oh, thank God. Yes. So it looks like the piece of metal gave up almost 1,500 joules of heat, but the water actually only gained 836.8 joules of heat. Where did the rest of that heat go? Into the cup. Yeah, so that means Q cal right? Whatever that difference is, 1496 minus that number, that cup actually gained 659.2 joules of heat, right, in this process. That's not our answer. We actually want CCal. So we can go ahead and take this number, set it equal to CCal times delta T, because that's that missing part. So CCal, calorimeter constant, delta T of the water. So I'm just going to put it over here in this corner. So the leftover heat that didn't go into the water, that went into the cup, so 659.2 joules equals CCal. Delta T of the water is 2. So it looks like CCal 2 Kelvin is whatever that divided by 2 is 329.6 joule Kelvin. So what that means is that for every degree that the water increases, the calorimeter also has to absorb 300 joules of heat. This is a really crappy calorimeter, right? Because water, it has a heat capacity of like, 4 joules per gram degree Celsius, but this calorimeter has to absorb almost 100 times that for every degree increase that water makes, right? So CCal and QCal is how we accommodate, that missing piece. We can measure how much energy is lost by certain systems. Well, the unexplained energy loss, that, there's not perfect heat transfer between your metal and your water, we add that element of the calorimeter having a heat capacity. That's how we can obey the first law of thermodynamics. Because really, if I said, your piece of metal loses 1,500 joules of heat, but your water gains 800 joules of heat, that violates the first law of thermodynamics. This is not perfect heat transfer. That heat had to go somewhere. And so in order to obey the first law of thermodynamics, we have to add this component of Q of the calorimeter, or CCal. And so that is very important in HCal and this chapter. Okay, is the higher the CCal or lower better for a calorimeter? So I like to think of it this way. Okay, so let's say Q metal equals Q water plus Q cal. If, let's say, your piece of metal lost 100 joules of heat, if this was perfect heat transfer, how much heat will your water gain? Based on the first law of thermodynamics, it should gain 100 joules. So what would a perfect calorimeter have as a calorimeter constant? 0. When QCal is 0, meaning that CCal is 0, that is a perfect calorimeter. Perfect. So a large CCal is actually really bad. That means that your reaction isn't doing efficient heat transfer. Okay, I thought that was important. So I decided to add it on the fly. Okay, so let's do the last chapter and then we'll be done. Remember, you don't have to say if you don't want to, but if you want to, then you can. I will just keep talking until it's 7:30 or until I run out of questions to do. So chemical kinetics, this is about how fast reactions go and how we can measure it. So the average rate of consumption of eggs is 4 eggs per minute. What is the average rate of production of cupcakes over the same period of time? So we can relate rates of reactants and products to one another by stoichiometry. So this has nothing to do with rate laws yet, right? That, okay, for 4 eggs will make how many cupcakes? 12, yes. And so the rates are related by stoichiometry as well. So for 4 eggs, you consume this every 1 minute. So I like to just use stoichiometry and recognize, every 2 eggs, you need 6 cupcakes. So if you cancel out these units, you see if you are consuming 4 eggs per minute, on the other side of things, you should be seeing an output of 12 cupcakes per 1 minute as well. So this is related by stoichiometry. We call these average rates or instantaneous rates. This has nothing to do with rate laws yet. It's just me relating, the reactants and products. If I'm consuming at 4 eggs per minute, what should my flour consumption be at that same time? It should be 6 flours per minute. All right. Okay, good. All right. So that is instantaneous rates. Just use stoichiometry. Next one. Given K is this for a reaction, what is the initial rate of the reaction when the concentration of A is that? So this is a rate law, it seems. So rate is equal to K times concentration of A to some order. Right? So I see, oh, I need to multiply K and concentration together, but I don't know what the order of A is. Should I just assume it's 1? We should calculate it. How can we figure out what the order is? I only give you a tiny bit of information. It comes from the unit of K. Yes. Right? So hopefully you recognize that rate has to be in the unit of molarity per second. So if you're multiplying by K, 6.2 times 10 to the negative 3 per second, so 1 over second. How many concentrations do you need to multiply to get this rate come out to molarity per second? What does the exponent have to be on this concentration? 1. If I put a 1 here, that's how I get rate in molarity per second. Or you can just memorize, oh, a unit of second to the negative 1 or time to the negative 1 is first order. A 0th order reaction is molarity per second. First order is second to the negative 1. A second order is molarity to the negative 1, second to the negative 1. Once you do enough of them, you like see the pattern, right? But that's another way you can know that this reaction is to the first order. And that's important because we need that in order to get the right value that comes out, the right rate. We need the right order. All right, so we're just going to multiply these two numbers together, get the rate, right? But getting the rate law in the order is important, and we get it from the unit of the thing itself. Because if the unit was K equals 5 molarity per second, and I told you, oh, initial A concentration is 10 molarity, what is the rate? First, tell me, what is the order of this reaction, if that's the information I give you? It is 0. Yeah, so what is the rate? 5 molarity per second. You don't even have to multiply by A because it's 0th order. So the unit tells us all. Okay. All right, consider a first order reaction with respect to A. It's 0 order with respect to B. So it might be best to write the rate law. So rate equals K times, I tell you, it is first order with A, 0th order with B. So this is the rate, and that's it. I tell you that the overall reaction rate is this when A equals that and B equals that. I want you to tell me what is the rate when A equals this and B equals that. So my strategy here is I tell you the rate in A at 1 condition. So that allows you to calculate K, then plug that into the second condition to figure out what is this new rate given these different concentrations. So notice that B is not in our rate law, so you can literally just ignore it. But if it was, then we would have to include it in this calculation. So let's just go ahead and plug in these things. So I tell you that the rate is 0.525 molarity per second when the A concentration is 0.1 molarity, since A is to the first order. So given this information, K is equal to 5.25 molarity per second. And then so we're going to write this equation again, rate equals K. So now we know what K is, 5.25 molarity per second. And now we multiply by this new concentration given this new system. So 0.25 molarity. And then that's your rate at the new concentration. Okay. Okay. Almost there. How many more? Oh, okay. Just a little more. All right. All right, consumption of donuts by Homer Simpson follows 0th order kinetics. What is the rate constant? If the rate constant of this 0th order reaction is 5 donuts per minute, how many donuts will be left after 4 hours? If Homer starts with 1,800 donuts. So I like to recognize, okay, this is a how much is left after a certain time. So I want to use the integrated rate laws, but I want to use the integrated rate laws for the 0th order reaction. So that one is what kind of concentration? Regular, natural log, or 1 over? Just regular. So A, concentration at some time is equal to concentration initial minus KT. I give you K. It's 5 donuts per minute. T is 4 hours. So I think, what is that? 240 minutes? Oops, sorry. 240 minutes is time. So we have time. I give you initial concentration, 1,800 donuts. So we can calculate how much is left after a certain time. This might look really similar to just like a velocity and distance equation, because it is. Okay, velocity and distance is 0th order. 1st order is acceleration and distance, right? Acceleration versus time. So there's a lot of similarities between physics, because this is technically calculus, but we just did all the math for you. So yeah, you just plug and chug that. You start with 1825 donuts minus K, so 5 donuts per minute times 250 minutes. Or sorry, 240, and then whatever that is. You should have how many donuts left? A lot. For 4 hours, you have 625 donuts. Cool. Still a lot of donuts. This is the episode of The Simpsons when he's in hell, and like the devil thinks he can torture Homer by force feeding him donuts. I don't know if you remember that episode, but that is what inspired this question. Okay. All right, let's keep going. So what is the order? Okay, so here's a mechanism. Which step of the mechanism is the slow step? If I tell you this reaction is 3rd order. So you might be like, what? You never done a question like that? You always give us the mechanism. Well, I did. But there's only 2 options of mechanisms I can give you. I can give you the slow step is the 1st step, or the slow step is the 2nd step. So why not just try them both and see which one is 3rd order, right? So let's do the first one, the easy one. The 1st step is the slow step. Hopefully you can just recognize what's the order if the 1st step is the slow step. It's going to be 2nd order, because if the slow step is the 1st step, the rate is equal to K times NO times O2. How many things are dependent here concentration-wise in our reaction? 2 of them. So this, if the slow step is the 1st step, this is 2nd order. So can this mechanism have the 1st step be the slow step? No. If we know that this reaction is 3rd order, we need to make sure the mechanism is consistent with our observation. So the slow step cannot be the 1st step. So that means it has to be the 2nd step, right? But let's check it. So let's say, so the slow step can't be the 1st step. It has to be the 2nd step, but let's check it. So if the slow step's the 2nd step, the rate is equal to K times NO3 times NO. So at first, this looks like 2nd order, but what's the problem? We can't have which one of those things? NO3, we can't have him because he's an intermediate. Okay, so to get rid of him, we're going to use the fast step and write out the chemical equilibrium. We say, oh, NO concentration times O2 concentration equals NO3 concentration. So this relationship, okay, and then the K's just kind of go away. What you want to recognize is that the concentrations can replace one another. And so we can replace NO3 with this part of our expression. So rate is equal to K times NO squared O2. So what is the order when the 2nd step is the slow step? It is 3rd order. So we could say, oh yes, the 2nd step is the slow step. Yeah. Oh yeah, I didn't want to put that. I just wanted to make 2 regular arrows. Yeah, that would be the giveaway. But what we should do, and yeah, so what I should have done is just made both of them just regular arrows. I adjusted this question from adopted it from like a different thing. They should be regular arrows because I don't want to give it away that the first step is the second step. I want you to arrive at it and you to recognize, okay, it can't be the first step because that's a second order reaction. So it has to be the third step. Yeah. Okay, 10 minutes. Perfect. All right. This is the same mechanism. Here's the balanced equation. NO is a what? Reactant, product, catalyst, or intermediate. So note where NO is. It's just right there, two reactants. So this is a reactant. But NO3 is a what? It's an intermediate because you see it. Oh, it shows up here, but then it's consumed in the next step. Catalysts are different. They cancel out of your reaction, but intermediates are produced, then consumed. Catalysts are consumed, then produced. Okay, almost there, y'all. Okay, here is method of initial rates data. Whoops. What is the rate law for this reaction? So if I told you that a reactant was second order, and if I said, oh, you doubled the concentration, what kind of rate change should you expect? Times 4. Yep. So we're just doing it opposite. We are observing how are we changing the concentration? How are we observing rate change? What does the order have to be? All right. So let's go through this. So the strategy here is look at 2 experiments where something remains constant and then look at the other thing. So I note here that B stays constant, but A changes. That allows me to recognize, okay, A is doubling, but B is remaining constant, so it's not affecting the rate changes. But how is the rate changing between experiments 1 and 2? It's increasing by a factor of 4. You can't tell, just put it in your calculator, do 5.64 divided by 1.61, and you see that the factor is 4. So what does that mean? The order of A must be 2. So it's one of the orders. Now let's get B. So I'm going to use experiments 2 and 3 and see, oh, look, between these reactions, B doubles its concentration, and then the rate does what? Doubles. So that means B is first order. So let's go ahead and just write that rate law. So rate equals K times A squared times B. That's the rate law. Now the second question is, what is the actual value of K? So how do we get K? We have the rate law. Plug in any experiment. Which experiment do you want to use? The first one, second one, or third one? You want to do the second one? Okay. So we're going to take all of the information in the second experiment, plug it into the rate law, and we should be able to calculate K. Here's the thing. If you got the rate law correctly, it doesn't matter which experiment you use, 1, 2, or 3, it should all be the same rate constant. If you don't get the same rate constant for experiments 1, 2, and 3, then you did something wrong. That's not the rate law, because that's the idea of a rate constant. So rate equals, so we're using experiment 2, 0.0252. Molarity, oh no, that's not right. My initial rate is 5.64 equals K. That's what we were solving for. A concentration, so 0.0252 molarity squared, and then B concentration 0.0125 molarity. I'm putting the units here because I need to make sure I get the correct units of K. So I'm dividing by a bunch of molarities. Technically, there are 3 molarities there. So I'm dividing by molarity cubed, and that's going to help me figure out what the unit of K is. So squared times 0.0125. So this number in the denominator is 7.938 times 10 to the negative 6. So 5.64 divided by that number. Oof, we get a really big number. Am I right? Dang, yeah, that's right. Okay, so K is equal to 7.1 times 10 to the 5. But the important part is the unit. See what's here. We have a molarity per second, and we're dividing by 3 molarities. So we're left with 2 molarities in the denominator and a second to the negative 1. So that is the proper unit and value of K. All right. Calculate the initial rate with these concentrations. Perfect. Now we have the full rate law. rate equals K times A squared times B. We know all the values now. We know K, given A, we know B, just plug them in. So 7.1 times 10 to the 5, molarity to the -1, second to the -1, that's K we just got. A is 0.075 molarity, and then B is that's squared, 0.01 molarity. And you see that the units should all cancel out rather nicely and get that. So the rate here, I think, is 40 molarity per second. Okay, last one. Maybe the hardest one. I don't know. I don't think so. All right. The activation energy of a reaction is 95 kilojoules per mole. The rate constant at this temperature is that. Estimate the rate constant at 75 degrees Celsius. Okay. I want you to look at the equation sheet and tell me, which equation should I use? I have activation energy. I have rate constants. I have temperature. This equation has activation energy. This one has activation energy. This one has activation energy. All three of these, but which one should you use? Not the left one. Nope. The middle one. Note here. Yes, I have activation energy, but look, I have a temperature and a rate constant. I have another temperature and another rate constant. So I will point out that you aren't completely wrong about using this second equation, because this is the equation of a line. But here's the thing, 2 points will always make a line. So we actually want to use this equation because it allows us to relate two rate constants at two temperatures using activation energy, because 2 points always make a line. These two equations are the same. This is like y equals mx plus b form, but this is 2-point slope form, which this one's just easier to calculate on your calculator. So we're going to actually use this middle one, where we just need to be really careful about our units and what we use. All right. Here, I give you a temperature. There's your rate constant. So T1, there is K1, rate constant 1. Here's T2. It's asking you what is K2. And then here's your activation energy. So you just got to be really careful in inventorying your values. So note here, activation energy is in kilojoules per mole, but it's best to put it into joules per mole. So 95 times 10 to the 3 joules per mole. That's what you want to use. I always like to take inventory of my values. So T1 is 25 degrees, so that's 298 Kelvin. T2 is 75 degrees. I don't know what that is. Let's get the T. Is 348 Kelvin. I give you K1, it is 0.15 molarity per second. K2, that is what we were solving for. So it looks like this is what we're solving for. We know everything else. Again, activation energy is given right there. It's 995 times 10 to the 3. So now it's just plug and chug. So natural log K1, so 0.15 over K2, that's what we're solving for. Activation energy, 95 times 10 to the 3 joule per mole over 8.314 times T2 inverse. So 1 over 348 minus 1 over 298. Okay, now you just got to be real careful with the math. So let's do, okay, do I have it down here? Yeah, so if I do all the math on the right side, I get natural log of 0.15. So I'm not touching the left side at all because I need to natural log both sides, or e to the both sides. So if you multiply all that together, you get negative 5.51. How do you undo a natural log? You take the e to both sides. So if you take the e to both sides, the natural log goes away. And so then you unlock that fraction, 0.15 over K2 equals 0.00405. And then you can, I don't know, do like some cross multiplication to get what K2 is. So you get K2 is equal to 37 molarity per second. And there we go, 2 minutes to spare. Thank you for joining me. So let's use our intuition real quick. Hot reactions go faster. So does this value of, what did we just get, 37? molarity per second. Does that make sense? At 298, the reaction goes 0.15 molarity per second, but at 75 degrees Celsius, it goes 37 molarity per second. Yes, hot reactions go faster. All right. So best of luck, everyone. Use those practice exams. Learn from your mistakes. If you get something wrong, figure out why you got it wrong so you don't make it wrong again. All right. Have a good one.